Let's consider this question. If the universe is infinite, and even if there exists a multiverse with an infinite number of universes, does that mean there's a copy of Earth somewhere out there? And even an exact copy of you, and perhaps an infinite number of such copies? We're just launching our channel, and this topic is a perfect way to kick things off. This idea pops up across all sorts of mass culture, in books, comics, movies, and TV shows. You can also find it in games and even songs, which makes it especially intriguing. Someone might argue that in a truly infinite universe, this is both natural and possible. We'll explore how realistic this is. But what's fascinating is the mental leap from the fact that Earth is, so far, the only place in the universe where life is confirmed, to the idea of infinite copies of our planet. It's a thrilling shift worth diving into. The thought that there's another you out there, living a slightly different life, might feel a bit uneasy. It can even be unsettling if you ponder it deeply. But if there's any basis to it, what does science have to say? Let's figure it out together. Could your copies really exist? That's what we're investigating today. Interestingly, the answer isn't straightforward. It has layers, starting with whether the universe is truly infinite and extending to the multiverse, which might come in several forms. We're just beginning to build our community, and this is a fantastic topic to discuss. That's what we'll tackle today, aiming to offer rough estimates of how far your nearest copy might be and whether you could ever meet them. Well, if they exist, that is, which we'll find out. I'm John, and you're on the Space Unraveled channel. We're thrilled to have you here. To keep things engaging, we'll weave in some cosmic curiosities along the way. What's neat is that this topic is full of nuances, with ambiguous and sometimes conflicting opinions. That's what makes it so captivating. Let's start with the first intuitive level that most people probably think of when they ponder this question. We'll dive into the basics right now. Imagine the universe is infinite, meaning sooner or later your copy would show up. This assumption seems logical at first glance. But then comes the question, is the universe really infinite? That's the core of our discussion. Short answer. We don't know for sure. Science hasn't settled it yet. There are estimates and guesses, but we're already making assumptions here. We'll stick to the facts. As you might know, this ties into the universe's geometry. Is it flat, open, or closed? This shapes all our conclusions. We'll break down what scientists say, and we'll keep it simple. Let's clarify what it all means. We'll start with the basics for clarity. When people talk about the universe's shape, they usually mean three main possibilities. We'll go over these in detail below. They say the universe could be flat, open, or closed. Each has its own quirks. The universe's geometry or space-time is a big deal in cosmology. A lot of science hinges on it. Whether the universe is finite and what its ultimate fate will be depends on the nature of space-time. Will it expand forever or collapse back in on itself? That's the big question. Visualizing how three-dimensional space can have a specific shape is tough for our brains. So we'll use simple examples. That's why we lean on two-dimensional analogies to get a basic sense of what's going on. It'll help us sort this out easily. When we talk about the universe's shape, the flat version often gets compared to a two-dimensional sheet. It's a classic starting point. Even though we can't picture it in 3D, we can draw solid conclusions. These are backed by precise scientific calculations. In a flat universe, two parallel lines never meet. That's a key trait of flatness. Draw a triangle in this universe, and its angles always add up to 180 degrees. That's geometry everyone knows. If you travel in one direction in this universe, you'd keep going away from your starting point forever. That's how infinite space behaves. This universe is infinite and expanding, meaning since the Big Bang, it just keeps growing endlessly. That's the first scenario we'll look at, and it's infinite. Just to be clear, the flat sheet is only a 2D analogy. We've tweaked it for simplicity. I can move forward, backward, right, left, and up, down right now. That's full freedom in 3 dimensions. The universe we live in is trickier than it looks. Take away my ability to move up and down, and I'd be stuck on that sheet. The simplification helps grasp the idea. In this analogy, the universe is like that, but it's not boxed in by 4 sides. It stretches out endlessly in every direction. That's how the flat model works in theory. And in reality, it's assumed to do the same, just in all directions. That's infinite expansion everywhere. The universe might also have an open geometry with negative curvature. That's the next option we'll discuss. This kind is called hyperbolic, and its 2D analogy is a horse saddle. It's another easy way to understand it. Parallel lines in one spot eventually spread apart. That sets it apart from the flat shape. In a giant triangle, the angles add up to less than 180 degrees. That's a big feature of an open universe. Here, the universe is also infinite, more or less. We'll dig into this more later. But the first hints of hypothetically seeing a copy come up in a closed universe. That's our third option now. It seems finite, though not quite the copies we mentioned earlier. There's a catch worth noting. We're talking about a closed spherical geometry, unlike the flat sheet. It's a whole different setup. Picture a 2D sphere surface, not a ball with everything inside, just the points equidistant from the center. It's a simplification for understanding. Still, it's just a 2D analogy. We use it to keep things clear. The key is that in this universe, parallel lines eventually meet at one point. That's the sphere's signature. A huge triangle's angles sum to more than 180 degrees. That's what makes it unique. Plus, this geometry means if you start moving in one direction, you could theoretically end up back where you started. Notice that's a cool effect of closed space. Imagine this universe was tiny, say 10 light years across. We'll explore this hypothetical case. Picture looking through a super powerful telescope in one direction. If nothing blocked the photon's path over 10 light years, we might see Earth as it was 10 years ago. It'd be like peering into the past. Somewhere out there, I'll be walking around from a decade ago at age 24. It's not really a copy, more like a reflection. Actually, it's not a copy, and it's just photons bouncing off Earth from 10 years back. That's an important distinction. Also, the geometry's quirks could make what we see look odd in shape and size. That complicates things. There's a great English article on this with awesome illustrations. I'll link it in the description. We suggest checking it out. But the universe isn't 10 light years across, and we don't see Earth copies or any space patches. Maybe it's about its size, or maybe the universe is so vast that light hasn't looped back yet. More likely, it's not closed. And of course, the three shapes I just covered aren't the only possibilities. There are other theories we'll touch on now. Some say the universe could be flat but finite. That's another cool idea. It might be shaped like a 3D donut, called a torus in cosmology, but we can't fully picture a 3D torus surface. So we use a 2D analogy again. Here, like the flat sheet, parallel lines stay parallel, not meeting or diverging. It's like the flat model, but different. Yet this space loops back on itself, making it finite. That's the main difference from an infinite plane. Move in one direction, and you return to your starting point. It's a closed loop in space. This applies to light too. If we lived on a 2D torus surface, and the universe was small enough for light to loop back, it'd have tons of ring-like paths to reach it. That'd create wild effects. We'd see copies of ourselves, and not just in one direction. In 3D space, that's hard to picture. Clearly, we don't see this, and the universe isn't that small. But if it were closed, its geometry could let us see a copy. Or rather, an image. Its real size wouldn't allow it in practice. Subscribe to Space Unraveled and let us know your thoughts in the comments. This blend of science and wonder keeps us curious about the cosmos. Now, the big question, what's the universe really like? We'll sum it up now. Scientists can't say with total certainty yet, but most data points to one option so far. It suggests it's like our first example, flat and probably infinite. That's the top scenario today, though it could be so huge that we can't spot curvature in our local patch. It feels flat like a sheet to us, but it might be a closed sphere. Some estimates say it's at least 250 times bigger than the observable universe. That's a mind-boggling scale to think about. Still, there's a decent chance it's infinite. And here, the multiverse comes up, at least in some form. The observable universe is like a bubble, a chunk with us at the center, about 46.5 billion light years in radius. We're just starting to probe these edges on our channel. We're not at the universe's center, of course. The bubble size just reflects where light has reached us since the universe began 13.8 billion years ago. These are core facts about our cosmic setup. Why is the observable universe's radius bigger than 13.8 billion light years? In short, blame expansion. Light doesn't just travel from A to B. It moves through ever-stretching space-time. We don't know what's beyond the particle horizon or how much more universe is out there. It's a scientific mystery. Suppose the whole universe was just a bit bigger than our observable part. There'd be no copies of Earth or us. It'd be too small for that. There's a horizon limit, and we're in a bounded section that's growing, but we can't peek past its edge. This is where multiverse talk starts. Famed cosmologist Max Tegmark came up with a classification with 4 multiverse types. The simplest, least debated one is the level 1 multiverse. We're in our observable universe bubble, shaped by us as observers at its center. If there's just more of the same expanding universe beyond, it's likely the same universe with the same physics and constants. Same galaxies, stars, and planets. A natural extension. If, say, 100 billion light years past our particle horizon, another observer exists, they'd have their own bubble. We're in the same space, but so far apart we can't interact at all. It's like living in separate universes, basically. This ties back to what we said at the start. Could our copy exist in such a universe? To get why copies might happen, Max Tegmark suggests this in his Multiverse Levels article. Simplify the universe to a 2D plane with just 4 particles. That gives 16 possible setups for those particles. If a level 1 multiverse has more than 16 universes, particle setups start repeating. Full copies of the first universe pop up. Now apply that logic to our universe, except it's 3D with way more particles. Picture a jar of colored candies. They're arranged a certain way now. How many shakes would it take to get them back exactly like that? Hard to fathom, but it's a solid example. In our universe, estimates say the observable part has up to 10 to the 82nd power atoms. That's the one with 82 zeros. Tegmark's article pegs subatomic particles at 10 to the 118th power. For a full copy of our observable universe, that insane number of particles needs the exact same arrangement, plus a matching history of interactions over billions of years since the universe began. It feels impossible intuitively, yet you could calculate possible setups. For 4 particles, or that huge number, then figure out how much space it takes for repeats. Tegmark estimates your identical copy would appear after 10 to the 10th to the 28th power meters. Punch that into a calculator, and it says infinity, though it's not really. It's a number too big to grasp. 10 to the 10th is a number with 10 billion zeros. 10 to the 10th to the 28th has even more. I won't even try converting it to light years. At that scale, meters or light years. A few zeros either way doesn't matter. After 10 to the 10th to the 92nd power meters, there might be a 100 light-year sphere identical to ours. After 10 to the 10th to the 118th, an identical observable universe. These are rough guesses, but if a matching universe region exists with your exact copy, the distances are so vast it's just food for philosophical thought. Some argue these copies don't have to exist, though. If you enjoy our content, subscribe to Space Unraveled and drop your thoughts in the comments. The vastness of space sparks endless debates among thinkers. The first multiverse level already feels mind-bending, but wait till we hit the second level. Today, open any Big Bang and universe timeline graphic, and you'll see inflation at the start. It's a key concept we'll break down now. Inflation is a big part of cosmology, and we'll cover its basics. It's widely accepted today, explaining some observed universe traits and cosmic issues. If the universe has been expanding since its start, during inflation, it grew crazy fast, exponentially. The inflation era lasted a tiny fraction of a second, from about 10 to the minus 36th to 10 to the minus 32nd second post-Big Bang. In that blink, the universe ballooned trillions of times, maybe more. Then inflation stopped and expansion slowed way down. But you might wonder, what's this got to do with the multiverse? The level 2 multiverse implies, if you will, infinite inflation. Yes, I said it lasted a moment, but in this idea, inflation keeps going outside our universe. It was there before our start. Imagine a massive space in constant inflation. In some spots, the hypothetical inflating field driving inflation weakens, slowing expansion. A bubble forms. That's our universe. It keeps expanding slower, forming stars, galaxies, and more. This bubble is an infinitely expanding level 1 multiverse, holding observable universe bubbles like ours. Yeah, there are lots of these bubbles, maybe infinitely many, separated by truly unthinkable distances. If distance even makes sense here, what's wild is that level 2 multiverses could have totally different conditions, different physical constants, even dimensions, maybe more than 3 spatial macro dimensions. Our universe has conditions where life could arise. Others might be totally unfit for it. Either way, the universe's scale grows even bigger. But again, if another multiverse has your copy, contacting them is impossible. Absolutely impossible. On copies, as I've said, opinions vary. An article by astrophysicist and science popularizer Ethan Siegel offers a different take. I'll link it in the description. In short, he crunches some numbers. He says particle interaction possibilities grow toward infinity faster than new level 2 multiverse universes appear. So, no copies. But now we're at the third multiverse type. Here come quantum matters. It's about the many worlds take on quantum mechanics. We're just starting, and this video is already long, so we won't go too deep. The gist is this. Quantum mechanics, describing our world at tiny scales, is one of today's top theories. Experiments back it up tons, but you've likely heard it's weird. A core quantum rule is superposition, meaning a quantum system can be in multiple states at once. It picks one state only when we measure it. Think of the famous Schrödinger's cat thought experiment, or a macro analogy, a coin that's heads and tails up at once. It decides which side when we look. At our scale, that doesn't work. It's just an analogy. Really, take an electron. Until we look, it's like it's in many possible spots at once. For a hydrogen atom, it's kind of like that. But when we look, it settles into one spot or state. The key is, in classic quantum mechanics, observing changes reality. It has a special role, which sounds odd. So some scientists back the many worlds view. In it, during a quantum experiment, say watching an electron, the electron's wave function doesn't collapse to one state. Instead, the universe splits into different universes where the electron has different states. So new universes form, not that it sounds less weird. A big supporter, cosmologist Sean Carroll, says this doesn't mean a new universe pops up every time you decide something. If you pick shawarma and cheese lavash, no other universe forms where you got the classic kind. There aren't infinite universes for every choice every being ever made. Universes split only with quantum system measurements. Still, Carroll says there could be tons of parallel quantum universes. They branch off, say, when an atom's nucleus decays, or you don't just decide but use a quantum random number generator for it. If this view's right, which we don't know yet, so there'd be loads of parallel universes with copies of you, maybe on different paths. That's the level 3 multiverse. Where are these universes? Infinite Hilbert, space with infinite dimensions. But that's a tale for later. The many worlds idea stirs debate in science. It has fans and foes, but it's a cool thought for sure. It's a chance your copies exist on a whole other level. I mentioned Max Tegmark's 4 multiverse levels earlier. The last one's a wild idea. Universes not just in different space spots, but with totally different physics beyond. Space-time, a universe akin to quantum effects, or where time jumps. We won't speculate more here. Yeah, all this is super fun to ponder. Some hypotheses and theories I've covered could be tested experimentally. That'd give firmer answers. At least if some assumptions hold true. Somewhere in the universe, another universe, or a parallel quantum reality, your exact copy might exist. We can't claim that for sure, especially since we can't even say if the universe is truly infinite yet. We've aimed to unpack this topic clearly on our new channel. Hope it was fun. If you liked this video, subscribe to Space Unraveled, hit the bell, and comment what you think of our content and how to make it better. Thanks for watching, and exploring these ideas opens up new ways to see our place in existence.